This video discusses color mixing for the Seeing the Light class. It is in place of our February 9th snow day class, and so watch the video, think about how it relates to the reading that you've done, try the exercises that come up in the video, and then we'll discuss it more after you post your class comments, class observations. We'll discuss it more in class on Monday. So coming up, we've got the next week, we're going to continue to talk about color and trichromatic vision, and then compare some color swatches with a Joseph Albers manuscript, Trip to the Library. The homework 2 is now due February 11th, February 13th, not February 10th, but the rest should stay the same. Remember that in general we have office hours Tuesday, Thursday, and Friday. Look at the email for specifics for this snow week. And with the class observations from last time, there were many great questions, and we'll go through them next time. So one thing that we talked about last time was trichromatic vision, and we're going to continue with trichromatic vision over the next few classes. What we discussed was that our vision has 3 cones, a short cone, a medium cone, and a long cone. And those the short, middle, and long, or short, medium, and long, refer to the wavelengths. And they're drawn here as blue, green, and red to give us an idea of what the primary colors are within those wavelengths, within those that those cones pick up. And we're going to see today, as we talk about color mixing, that our color schemes to describe colors follow the same blue, green, and red combinations. So this RGB, red, green, blue color model was developed in order to add together 3 specific colors to reproduce a big range of colors. And notice that in red at the bottom here, I've written RGB system is designed for combining light. It's designed for combining light, not paint, for example. So the name of the model, the RGB system, comes fairly simply from the initials of red, green, and blue. And the purpose of the RGB color model is to represent or detect or display images in electronic systems, televisions, computers. Computer would be the primary place that you would see it now because of all of our digital imaging and modeling. So many of you are in graphic design or other kinds of environments where you use computers to model color. Therefore, the RGB system is important for you to think about. Before we had computers, though, or so much of it, there was an RGB model that was still based in the human perception of colors, as we talked about on the last slide. So the RGB values specify how much of red, green, and blue are in a particular color. Let's take a quick look at a color converter. This is just a way to say, what are the RGB values for a particular color? You're welcome to play with this yourself. You can see the URL in the top of the screen. So, for example, here we've got a color orange. Let's look at the red, green, and blue values, 250, 132, and 14. What if we made that 14 the same as the other color values? What do we have now? Well, it looks pretty red, so it's mostly red. Tiny bit of green, tiny bit of blue. And we could make those both 0. It's not going to look very different to us because our color differentiation doesn't change by that much, but there you have it. If we make equal red and green, we get yellow. If we make equal red, green, and blue, we get white, which we'll talk about in a moment. If we make equal green and blue, we get cyan. And equal red and blue, and we get magenta. So we can do a lot of color mixing and color representation here. There's a number of things we can play with. We'll come back to that. I encourage you to use it yourself to experiment with how the different values, different amounts of red, green, and blue change the color that you're looking at when you combine colors additively. So Notice that in that case, having 0 of all the colors would give black, and maximum of all the colors would give white. So when I put 250, 250, 250, we got white. And if you put 0, 0, 0, you would get black. This is referred to as additive mixing. So we're going to look at this combination, combining colors numerically. Our colors that we're dealing with, we can either call them completely red, green, or blue, and we'll refer to that as fully saturated, or some combination of red, green, and blue, or in the families in between. All right, so we're going to label our colors as with their relative proportions of red, green, and blue. So R, G, and B, we'll write each R, G, or B as a percent of the total. Let's give an example here. So, well, that's not a terribly exciting example. 0, 1, 0 means 0 red, 100% green, and 0 blue, which is saturated green. Sorry about that. And so just to remind you about percentages, when we say a fraction or a value of 0.3, that's the same as 30%. So 0.3 is out of 1, and that's the same as 30%. So an example, if we have 3 numbers here, let's say red is 0.2, green is 0.3, and blue is 0.5. And we want to find its primary hue. So 0.2, 0.3, 0.5. We want to see what are the strongest colors there. And you can just kind of look at it and figure it out. But an easy way to do it mathematically is to pull out the gray component, subtract out the smallest component. So here 0.2, 0.2, 0.2 is the smallest component. And then we have 0, 0.1, 0.3 left. What's left here is 0 red, 0.1 green, 0.3 blue, which is in the cyan family. Let's test it out. So 0.2, 0.3, 0.5. We can't really do 200, 300, 500 because we can't go over 255. So instead we'll do 100. I'm just dividing everything by 150, and 500 was the same as 250. All right, so this is the same as the color that was just specified. It would be in the cyan family. It looks like, well, apparently it's called cornflower blue. Looks nice and blue. And it should be the same as 0, 100, 300. Let's see how that looks different. 0, 100. I can't do 300. Okay. Let's do 50 and 150. Interesting. So this is a much less saturated color, but it still has the same ratios of red, green, and blue. All right, so this example, when we say find the hue, what we're looking for is what's the most saturated component. Is it only red, only green, only blue, or a combination of the two? So here, let's do one more example, and I encourage you to pause and then go on from here. So if we shine white light through a filter, and it gives us an RGB value after the filter of 0.5, 0.1, and 0.4, what's the hue? So pause here, I'll continue on and discuss the answer. So the RGB that we're given is 0.5, 0.1, and 0.4. If we take out the smallest component, we have 0.1, 0.1, 0.1 plus what's left, which is 0.4, 0, and 0.3. The combined colors, the two colors that are still present are 0.4 and 0.3, and we call that a magenta hue. In other words, it's red and blue. Now, my cheat for what hue I'm looking at or what color I'm looking at is the little color wheel or color circles up here, kind of like a Venn diagram. And if I say, oh, if all I've got is blue and red, when they overlap, I get magenta. What if I only had red and green? That would be a yellow hue. if I had green and blue, that would be a cyan hue. So that's what this wheel, or this combination of colors, it's not a color wheel, is showing. We haven't talked about the color triangle yet. You did in your reading, but you would see on the color triangle, it would be a reddish magenta. And the saturation level tells you how strong the color is, how strongly saturated it is. So in this case, a lot of the color is gray. It may not look terribly strong, terribly saturated. Right, so the language we're going to be using primarily to discuss additive color mixing is the color triangle. And we know that the three additive primary colors are red, green, and blue. So the color triangle has red in one corner. I'm sorry, I just pointed at the green. Red in one corner, green in another corner, and blue in the third corner. Red, green, and blue. And all the colors in between. The complementary colors, the main complementary colors are cyan over here between blue and green, magenta, which is between blue and red, and yellow, which is between red and green. So our colors in the color triangle are identified by specifying a fraction of green and a fraction of red. And it really becomes quite easy to read off of the triangle. There isn't any, let's say, mathematical processing that's happening. We're simply reading off of this triangle as if it's a plot. So what we read is the fraction of green and fraction of red. We'll do an example in a moment. And there's only a fraction of green and fraction of red. Well, all three fractions must add up to 1. So whatever is not green or red must be blue. This is an example to show that different kinds of saturation actually will give us the same hue. All of these pairs are different saturations but the same hue. So these two greens are the same hue. They're just different saturations, same proportions. One of the ones I like best is the orange. That orange and brown are really the same hue, even though they look very different, but they have the same ratios. Just orange is a more saturated color than brown. Beige, I believe, is also the same hue as orange and brown. Gray and black are the same hue as well. They have equal amounts of red, green, and blue. All right, so let's use this for an example of our color triangle, using our color triangle, and then also discussing complementary colors. The color triangle here, let's suppose we wanted to find this one called SB. What is this SB? It actually stands for spectral blue. So I would look here and I'd find the fraction of red that dot seems to have. So I drop it down. It looks like I have 0.1, 0.15, 0.16 would be the fraction of red. And then over here on the green axis, I've got 0.1, 0.15, 0.16 as well. 0.16, 0.16, and let's do this. So our red, green, and blue, we've got 0.1. Right. 0. Doesn't want to do a point for me. 0.16. And then I have, this is what you're writing down too, I have 0.16 of green. Right. And now how much blue is there? Well, it's going to be 1 minus the red and the green. So red plus green is 0.16 plus 0.26, 0.32. 1 minus that is 0.68. So let's say 0.68. All right, let me close our parentheses. We've got red, green, and blue for that particular color, for that spectral blue color. In order to find the complementary color, we simply look through red, from that color through white, over to an equal distance past white to another color. So let's describe that more on the next slide. This is the same kind of picture. The picture on the left is our color triangle. The picture on the right is just something different. It's not exactly a color triangle. Don't use it for the color triangle. Here, let's look again at this. The complementary color is a color that adds to our color to make white. So we want to add to spectral blue to make white. When we start with spectral blue, the thing that will add to it, is whatever is an equal distance past white. So I would take out my little ruler or just make a rough estimate of the number of squares I've gone through here to white, go an equal number of squares past, and I would hit yellow. That means yellow and spectral blue are complements. And I want to mention here that yellow and this point here, blue, are not complementary colors. In fact, it's yellow and this color, blue. So it's important to be careful about which two colors actually add to make white. What we're going to see, we're going to do this exercise briefly. When you look at an afterimage color, what you're seeing is a true complementary color, like what the color triangle would show you. So if you stare here at the center in between the blue and the green, we'll stare at it for a while. What we'll see when we look at a white background in a moment is we'll see the true complementary color of blue. In other words, what color would be added to blue to make white? And then the true complementary color of green, or what color would be added to green to make white. So you can see yellow and magenta. So blue plus yellow, that particular yellow makes white, and green plus that particular magenta also makes white. Try the same thing here. Pause, look at it for a while, and then go on to the next slide. And you'll see the true complementary colors of those two, of red and yellow. This is a more fun example. If you stare here, you have to do it for quite a while. So you look at the dot for about 30 seconds, pause here for about 30 seconds, and then when you finish, after quite a while, go to this slide. And what you'll notice is that the slide looks like it's in color, but it's actually not. It's actually black and white. And your afterimage color is overlaying on this one to give it color. So go back and forth between those two slides and see if you can get the effect to work. All right, try this exercise on your own and bring in your answers to class. So pause here, try the exercise, draw it, not on a whiteboard, probably, and bring in your answers. Something interesting about the color triangle is that it only includes colors that can be made by mixing red, green, and blue. This sounds like it's just one sentence, but it's a very fascinating sentence. Okay? The colors that we can see is much bigger. Well, quite a bit bigger. So look at this picture. It's got this like horseshoe-shaped thing around the triangle. The horseshoe is all the colors human vision can see. The triangle is all the colors we can make by mixing red, green, and blue on our computer screens. In other words, the colors out here on this computer screen actually aren't the true color. We could see them, but we can't make it. So you're actually not looking at the color that should be out here. This is just, it gives you an idea of what we're talking about. This is a picture that's very similar. Take a while, pause here, and read the little text boxes that describe it. It's the same type of picture. It's a color triangle within the total range of colors that you can see. And I'll go on. Now, that was all about additive color mixing, or adding light. And subtractive color mixing is when you either reflect light or filter light. In both cases, you're doing subtractive color mixing. The subtractive primary colors are cyan, magenta, and yellow. You'll see CMYK as being typical paint colors. That's cyan, magenta, yellow, and black. Those are subtractive primary colors. And they absorb or they filter their complementary colors. So those three subtractive primary colors would absorb out the complementary colors. Cyan would absorb red, magenta absorbs green, yellow absorbs blue. This color mixing is called subtractive because what's happening is we're taking out colors instead of adding to colors. So when you put a filter in front of a light, you're taking out colors that are subtracted by, that are absorbed by that filter. You can try this FET that gives you just a very basic look at what happens with filters. And here's a visual representation of what happens with filters. Let's say you've got all colors coming in from the left and a magenta filter. The magenta will absorb everything except for red and blue. Red and blue add to look like magenta to us. So it's what we see through that filter is magenta. If we have all colors shining on a cyan filter, it will absorb everything except green and blue. And so green and blue will add together and we'll see green and blue, which will look like cyan. And similarly, a yellow filter will absorb or subtract out everything except green and red. And so what we'll see is yellow. If you did a sequence of filters, you could block all colors. Because suppose in this case you started with a yellow filter and it will let red and green through. And then you have a cyan filter, it only lets green through. And then you have a magenta filter, well, magenta blocks everything. So theoretically, you would get no color coming through that filter combination. All right, so in summary of subtractive color mixing, when you add up yellow, magenta, and cyan, you get black. Yellow and magenta would add subtractively to give you red. In other words, a yellow filter and a magenta filter will only let red light through. A yellow filter and a cyan filter will only let green light through. And cyan and magenta will only let blue light through. In comparison, these two color mixing Venn diagrams show what happens when you additively add colors and subtractively add colors. So in summary, additive color mixing is adding wavelengths to make a new color. And we see that in computer screens, TV screens, and point-to-list paintings. Subtractive color mixing is when you take out wavelengths to make a new color. And we see that when we subtract by reflecting off of paints or colored objects, which absorb colors except for what we're seeing. We looked at that last time with the spectrometer. And with color filters, we subtract by absorbing out colors that aren't the color of the filter. So that's the summary of where we're at right now. Submit your class observations tonight. What I recommend is that you try those exercises that came up during the text. You could submit your answers. So you could say, well, I found this color and give the RGB values, and its complement looked like this in the color triangle, for example. You could use that for a class comment, or comment on what you think, if this helped to clear up anything, or just add more confusion. Because the difference between a video and in person is you can't actually ask questions. So we'll see you next week.